Hello, my name is Meghna Mariam Anil, and I'll be talking about understanding stable models. Now, we have propositional programs. So, propositional programs are sets of logic based rules or statements formed with propositional variables and logical connectives. These programs are used to represent knowledge in a way that a computer can solve through logical reasoning. Now, we have positive propositional program, which is a type of propositional program that exclusively involves positive information, meaning it contains no negation, which is not or the symbol. These programs are simpler to analyze because they inherently avoid complexities associated with contradictory statements. Now, if I take an example, a positive program might include rules like if P then Q, or if P and R then S, without any negation, such as like an example of negation would be if not P, then Q. And if you look at the right side of the screen, you'll be able to see the basic um, propositional logic that we use. Now, moving on to stable and minimum models, we will start with a stable model. So, now a stable model is of a propositional program. It is a set of propositions that satisfies all rules of the program and is minimum. So, no subset of this set can satisfy the program. Now, if we define minimal models, a minimal model for a propositional program is a set of truths such that no smaller subset of the model still satisfies all the rules of the program. There is also equivalence in positive programs. So, if we say in positive propositional programs, which are those without negation, every minimal model is also a stable model, which can be noted, and it's also vice versa. This is because the absence of negation simplifies the logical structure, making every minimal model inherently stable. Now we're gonna do a step-by-step process of constructing the minimum model of the program that's shown on the left. Now first we start by identifying the ground facts. Now if we look at it, the statement R1 is given directly without any conditions. This means R1 is a fact and is true in the model. Next step is to propagate true facts. Now, the next statement is Q is true only if R1 and R2 are true. Since R1 is already true and is part of the disjunction, Q1 is also true due to this rule. Now, the next step is to do further propagation, which is the first statement is P1 and P2 is true if Q1 and Q2 are both true. So here we can see that Q1 is true, making the disjunction Q1 and Q2 true, which implies both P1 and P2 are true, since the entire conjunction must be satisfied for the implication to hold. Then we have our completion. So after evaluating all the rules, the model includes P1, P2, Q2, and R1 all being true. So there's no information provided about R2 or Q2 other than their involvement in implications. Since Q2 and R2 are not needed to satisfy any of these rules based on other established truths, and there are no rules explicitly setting them to be true, they remain false in the minimal model. So we can conclude by saying that the minimal model of this program consists of P1 equals to true, P2 is true, R1 is true, R2 is false, and Q2 is false. The model is minimal because no subset of these assignments satisfies all the rules. Moving on. Now we can use Klingo. So Klingo is a popular answer set programming tool that we are all very aware of. So now we will do syntax conversion from propositional logic to Klingo. So in propositional logic, we might express a rule like if P then Q, as P is true, Q. In Klingo, this would be represented differently, meaning Q is true. If P is true, it will be represented differently. So now if we look at the sample Klingo code on the screen, we have our question. So from what we get from trying out, this output that we get indicates that the model where P, Q, and R are all true is a stable model of the program. Next, we have negation in propositional programming. So we have something called as critical parts. Now, critical parts of a propositional formula or rule are subformulas that begin with negation. They are crucial because they determine how the overall formula behaves under different interpretations. Now, like example in the rule, P is true, negation Q, R, Q, sorry, not Q. So not Q is a critical part. Now, let's define reduct of a program. Now, reduct of a propositional program involves it's a propositional program relative to an interpretation in a new program derived by simplifying the original based on the truth values given in the interpretation. Now, this would involve things like removing rules with negated components that are false under the interpretation, eliminating the negation in rules where the negated component is true. Now, if we look at the example on the left, we can see that P is true if Q is not true, and Q is true if R is not true. And then we see R is true. So if we look at the result, we can see that it results in R as the interpretation. Now we can determine stable models with negation, which is to determine if the interpretation is a stable model. We compute the reduction of the program relative to the interpretation. So we check if and then we check if the interpretation is a minimal model of this reduct. That is, if it satisfies the reduct and no smaller subset of it does. Thank you.